And here we go with problem 617. This is where we start getting into t statistics. What is a t? T is like a z. Okay, so remember what a z is? Okay, so t is like a z adjusted for a couple of things. One of them is if we do not know the population standard deviation, if we do not know that, and otherwise, if we have a low number of sample data, if the size of the sample is not very big, we'll go to that, especially when it goes less than 30, when your sample size goes less than 30. Okay, but in this problem here, we're using the first situation. So the other one was sample size is less than 30. Okay, and what happens is that some errors get introduced because the of scarce data on that. Okay, it starts degrading as you go below 30. It significantly gets degraded as your sample size goes below that. So just think about this. This is like a magic number in survey work when you have surveys that come back in statistics. The derivation of it is left out of this course. The book avoids doing the derivations on these types of things, and it actually has a very concise and great description of degrees of freedom. What does that mean? Okay. In the simplest case, it means that if we know the average of a group of numbers, 2, 3, and 4. Okay, so just by inspection, we know that the average is 3. But in cases that we couldn't just inspect it, we actually had to calculate it. If we knew what the mean of this was, if we were given 3, okay, we could ignore one of the points. Let's call it this. In the absence of one of the points, we could solve for it because we already know the mean. And that's where you basically lose a degree of freedom. It doesn't give us any new information, okay? Because we can get rid of any one of these numbers and come back to it, okay? So that's why there's a sample size is 3 here, where we would go to n minus 1 is equal to 2 when we do sampling type things, when we have something like the standard deviation. It's just that we're overestimating because we'll have an extra number in here that we don't need. It's not an unknown. We want exactly the numbers of pieces of information that it takes to define something, and we'll have one extra degree of freedom unnecessary here. That's why we go to n minus 1 is equal to. The book has the most precise description of degrees of freedom that I've seen. It's an extremely pragmatic book. Okay, so you'll notice in the equation out of the book 6.3 that the alpha here, we always have to keep mindful of the alpha is given as, if we want a 90% confidence interval, the alpha would be 0.10 on that. And the reason why you often and always see this alpha over 2 is because we're describing a two-tail problem. Okay, so half of your alpha total alpha would be alpha over 2 would be down here in one tail, and the other half would be up here. That's why we always reference this t half of alpha. And notice in this, as opposed to the previous problem that we had, we have to keep mindful of the degrees of freedom as n minus 1. So in this problem, what do we have? A sample of 42. Okay, so let's put some numbers in here. Sample mean is, I have to pull it out, I can't quite see it over there. 2.56 visits to the restaurant, 2.56. Standard deviation of our sample, okay, so we have the sample, and they're interested in a 95% confidence interval, so we know we're going to need alpha somewhere in here. So 95.95, 1 minus 0.95 is equal to your alpha is equal to 0.05. Alpha over 2 is 0.025. Okay, so we're just going to establish that up front and not forget it. Sample size of 42. Okay. So with this information, we can figure out what t is. Now, remember, t is like our z, but it's an adjusted for z for when we don't have the population mean, or we have 30 or fewer than 30 samples, 30 or fewer samples. Okay, so we can use the table over here out of the back of the e-text I got. I took the screenshots from it. And so we need to go over to alpha over 2 is 0.025. Because it's specifying the upper tail area, we come up here with 0.025. Go to line 41 here for 41, 2.0195. Okay, so that's our t that we're going to use up here. Okay, we evaluated at alpha over 2 and minus 1. Okay, so then we have to get our margin of error here will be that times this adjustment factor, which is going to be the standard deviation of the sample over the square root of the number of samples that we took. Okay, so we're going to use Excel to do the same thing. It's going to be equal to t dot inverse of, and you need to put the whole probability in there, not the alpha over 2. You need 1 minus alpha over 2, which is 0.025. Degrees of freedom is 41, and we get 2.0195. Okay, it's rounded off to the correct level that the table gives us there. Okay, so all this now says is going to be the mean. Getting pretty good at this. Mean, the lower claim, C limit would be minus that times, we have to put the adjustment factor in there, which is our standard deviation divided by the square root of 42. Okay, so that's not n minus 1. I'm going to put parens around everything here that I need to be really nice to people downstream from me that might read this, so it's more easily read. You don't have to depend on order of operations there. Let's just see b3 square root of b14. Just make sure that this is correct. Yes. B13 is over that. And it looks like I have an extra set of parens. I don't really need it there. That's what it is. Okay, so that's the right number. So the lower is 2.058, and the upper is going to be, I'm just going to take that equation, Control C, drop it in. So if we draw that, our range is 2.058-ish to 3.06-ish. 2.56. Low end is 2.02. I'm going to shorten these up so I can fit them in here to 3.06. That's our margin of error at the 95% confidence level. So problem 619, if you grab the data for this, you're going to see that this is just practice at different confidence levels. You're going to get the same confidence intervals, or you can use confidence intervals for GPAs here. It's just some extra work. 1, 2, 3. You're just going to run it 3 times like we just did in 617 using the data. So that's really all that I need to advise on this. Okay, in the first part here of problem 21, we go back to the credit table. So I have the actual file open, the original file open here, but you are also given that information while you're doing the problem. You can download it as an Excel file. When you download that, all you are going to get is, it's not being shown here, all you're going to get is the checking and savings data. That's it. You're going to get that's all the Excel file that gets downloaded has in there. You have to do the total now because the problem says we're looking at the total. Okay, so the problem says treat the records in the database as a population. That means everything, of course. Okay, so use the accompanying sample credit risk data to compute the 80, 90, 99% confidence intervals for the mean total assets. Control C, held in the bank by applicants using, okay, so they give us this sampling distribution formula that we've used before, but now we're using it more in a real world situation. Use that in any appropriate Excel functions. So you could calculate it this way, which we'll do, or you could go back and just use the confidence.norm formula. So explain the differences as the level increases. So we're going to pre-explain it, okay? So when you have pretty widely varying confidence intervals of 90. So we're talking about a range, okay? So it says that if we want a at a confidence level of 80, I'm going to draw these on top of each other. Actually, is a better way to do it. Okay, so we're going to draw a probability of 80, and so our sample is like this. Okay, and what we're doing now is we're varying the confidence level that we want in this. Okay, so what is that going to do? If we want, you know what, 80% of the time, our sample, okay, will contain the mean of the population. Okay, that means 10%, 10%, 80%. Okay, so 80%, what you want to do is think of this as a stake in the ground. Okay, so the stake in the ground is the actual population, all right, is the actual population mean. All right. And what we're doing is we're taking this curve and we're sliding it back and forth, right? And so it says what's the range? If you really think about it, is at the very low range. Wasn't a very good vertical line. Mean. Okay, so at the low range, we can be our mean can be very high in our sample, all right, to the point that the actual mean will be lying right on the very edge of this 10% part of the lower 10% of the confidence interval, the lower bracket. Okay, so again, I'm going to draw it again, and that's where we're going to put the stake in the ground. That's the mean of the population, and what we're saying is that it's as if we're taking this is like the low end of our mean. Okay, under the conditions of 80% confidence interval, what we said is that our mean can be as low as this down here or as high as this up here. So it's just touching the edges of those edges of the confidence intervals. Okay, like that. All right. So if we want to capture, 80% of the time, we will have something that looks like this. Okay. Now, we're going to pre-solve the endpoint of this. What if it's 90%? If we want to capture it 90%, right? What we have to do under the same conditions, the same number of sample points that we took, okay, so samples of readings, we have to spread it out. We have to go wider. We have to say that the range is actually going to be wider, okay, to be able to contain that. So we have to spread the confidence interval from 80. This is when it was done at 80%. This is when it was done at 90%. And guess what? Of course. And it says if we want a margin around our sample mean that captures the population mean 90% of the time, it's going to have to be really wide spread out. Our endpoints, the range has to be really wide. It makes logical sense. Hopefully, you catch what I'm saying here. Is you have to broaden the range. So, well, okay, we have to when we want to get 99% correct, we're hedging in a way that you can think about this as hedging. Oh, okay. Well, wait a minute. If you want me to be at 90%, then okay. So let's say there's money on the line here, right? And so on your own personal money, so you go, oh, you're going to hedge. You're going to, oh, wait a minute, I'm going to broaden my range out. I'm going to push the points out. Oh, you want me to be right 99% of the time, Mr. and Mrs. Boss? Okay, then I'm going to hedge even further. How long is your project going to take? Okay, and it says this says you better be right. You're betting your career on it. And this one says, hey, good enough. I'm on the phone with somebody. They just want a rough number. Okay, but this one is down to brass tacks, dollars, and profitability is really measured. It's very, we're at a problem where one slip up and we can lose money on it. Okay, so that's basically what you want to be 99% correct. That's what we're doing here in this problem. Okay, so let's go back here. So I use the original file here, but you get the same data by downloading it in the homework problem. All right. So I set up a table over here. So our confidence intervals, the first attack on this is from the standpoint that we do know, this is that we do know the population mean. We do know this. And the second part, right? So that's where we can use Z. We can use the Z uh, score. We can use Z here. And the second part is we do not know, as in, whoops, Control Z. I'm at the edge of my writing ability over on my pad here. No, we do not know, as in no, we do not know the population mean. Okay, so what? We have to use T. We know that. That's a degradation of the degradation basically of the z. It takes into account that we're flying blind here. We don't have any population mean, or we have fewer than 30 readings in our sample. Okay. All right. So I'll just step through this. We already did these problems. You're going to do one problem 3 times, and I already pre-explained why it gets wider. Why does the confidence? So we're going to look for that to happen. So the sample mean. Okay. Our sample mean, we go over here on the right, I'm going to edge over a little bit. I can get everything on the screen this way. I think it's fine. Yeah. Okay, so I can see my total column over here, this orange gets used to generate what's the total average, what's the average of the total, okay, and what's the standard deviation of the population. See, we have that in this problem, and we can use it. That's how we can use the z, right? But in our sample, our shorty sample here, that's the other file you download with the problem. It gives you an average, and we have a standard deviation associated with just the sample. So let's take a look at how to solve this. So our sample mean is $2,026. Okay. Our population standard deviation, population is 4,821. Okay, so that's the variability. The population size is 20 for the purposes of our z. Okay, so what's the z value on here? How do we calculate the z value? I'll go into that. All right. So just like we did in the other formula or the other problems, we use the formula norm dot s dot inverse. So we give it a percentage and it gives us a z value. Okay, that's how we're calculating the z. Because remember, we're going to degrade that, right? It's z times this, right? So whatever the z is like the free world, unencumbered edge that we use for this mathematical property of normal distribution. Okay, so we're applying, we're leveraging all the properties of normal distribution in our sampling world. We're sampling, we know that the sample means perform close to a or exactly to a normal distribution. That's why we're exploiting the properties there. That's why we drill into the normal distribution so much in these classes. Is you're using it a second time here, not just on the population, but on the sampling distribution. Keep that in mind. Okay, so we're going to degrade the z by the standard deviation, and that it is what it is. Okay, and it has to do with how many sample points we take. Okay, right. So it's x plus and minus this is our degradation. That's what we're shooting for here. Okay, so we got our z value. Okay, so now what I did is I calculated the sigma over the square root of n. Okay, that's what this next line contains. Right, and we can get our margin of error. Okay, so this is our margin of error. That's all I did is just multiply those two things together. You can see here, multiply them together, and you're home free after that. All you have to do is subtract. Whoop, Control Z. I blew it away. Okay, so all you have to do is subtract that margin of error from the mean and add it to the mean. Okay, and then once we understand how to operate with the primitives here, which is extremely important, that's why we go dragging through this, is to make sure that as you use these formula in the real world, if you go out and you have some kind of odd result, that you can back down from using the power Excel formula that they hand us that are just so powerful. You got to be careful because they have a lot of energy in them. And if you don't know what happens, it can really send you flying because you might trust a number that shouldn't be. You should be always questioning the numbers that you're looking at here. But to use the Excel formula here, okay, I'll just get this out of the way here. Okay, so what I did was I used the confidence.norm formula, which is kind of lazy and sloppy because you just give it the alpha. You're not even worried about the alpha over 2 in this formula, and you run the standard deviation and you run the sample size there. So you put that in there. Okay, and we should get the same number, 644 3408. Okay, so that's how you wrap that one up. Just double check, make sure that everything's working. Okay, it's really important in data analytics to know what's going on underneath the covers here. And before we go on to the next part of this, where we do not have the population information, okay, what we want to take a look at is if we look at the numbers here that I just explained back on this page. Okay, so I generally explained it here, and now we can actually see it. That when we say 80%, all we need is 80% of the time that our brackets contain the mean of what the bank account is total of checking and savings for these people applying for loans. Let's assume that's what's happening here, right? So if we look at it, the range here is six at 80 is 644, and on the upper end is 3,400. And when we say, hey, listen, now we got to sharpen it in. What do we think the mean is of these? But at a 90% of the chances, 9 out of 10 chances, when we use this logic, we actually capture the mean of the total, total worth of each of these people that are applying. Okay, notice how it gets wider. So this on the for 90% goes lower than the previous one, and on the high end it goes higher than the previous one. So when we increase, oh well, we need to have a wider margin to capture more probability that we're going to get the meaningful in our sample to the actual population mean there. Okay, so now we'll move on. Let me get rid of some of that. I'll just get rid of that one. We're going to move on to the other problem that we have here. Okay. Okay, so I'll show you the numbers here. I think it helps if I do this step by step. Okay. Sample mean still stays the same. Sample. Now we're using the sample standard deviation because we don't have any information about the population data. Sample size is the same. T-value. Okay, T-value. We're going to be using the margin of error around the mean is T evaluated at alpha over 2, comma, and n minus 1. Okay, that's when we do the sample, and it's uh, multiplied by a modulating kind of factor here of s over the square root of n. Right. So our sigma, our t-value, I'll show you the formula there. T inverse is equal to 1 minus half of alpha. We need a probability in there, okay? And we put in the degrees of freedom, which is the number of readings in a sample less 1, okay? All right. Sigma over the square root. So all I did was take the sample standard deviation now and divide by the square root of n, which is 20. Okay. Our margin of error is going to be this part here. We're going to take our t and we're going to modify it by this effect of the number of sample points that we have, or how many readings within that we have. Okay, so our margin of error comes out as 879.83, and the confidence interval lower is just the mean minus that, and the confidence interval upper is just the mean plus that. There you go. Okay. So that should wrap it up. I think that's everything you need for 621. And I'm going to wrap this one up and post it as a new video.